Okay, well, here we're at the beginning, and I think it's worth thinking about what we know, calculus. Differential equations is the big application of calculus, so it's kind of interesting to see what part of calculus, what information and what ideas from calculus actually get used in differential equations. And I'm going to show you what I see, and it's not everything by any means. It's some basic ideas, but not all the details we learned. So I'm not saying forget all those, but let's just focus on what matters. Okay, so the calculus you need is my topic. And the first thing is you really do need to know basic derivatives. The derivative of x to the nth, the derivative of sine and cosine, above all the derivative of e to the x, which is e to the x. The derivative of e to the x is e to the x. That's a wonderful equation that is solved by e to the x. dy dt equals y. We'll have to do more with that. And then the inverse function related to the exponential is the logarithm, with that special derivative 1 over x. Okay, but you know those. Secondly, out of those few specific facts, you can create the derivatives of an enormous array of functions using the key rules. The derivative of f plus g is the derivative of f plus the derivative of g. Derivative is a linear operation. The product rule, fg prime plus gf prime. The quotient rule, who can remember that? And above all, the chain rule. The derivative of that chain of functions, that composite function, is the derivative of f with respect to g times the derivative of g with respect to x. That's really it's chains of functions that really blow open the functions that we can deal with. Okay, and then the fundamental theorem. So the fundamental theorem involves the derivative and the integral. And it says that one is the inverse operation to the other. The derivative of the integral of a function is, yes, here is y, and the integral goes from 0 to x. I don't care what that dummy variable is. I'll change that dummy variable to t, whatever. I don't care. T to show the dummy variable. The x is the limit of integration. I won't discuss that fundamental theorem, but it certainly is fundamental, and I'll use it. Maybe that's better. I'll use the fundamental theorem right away. So, but remember what it says. It says that if you take a function, you integrate it, you take the derivative, you get the function back again. Okay, can I apply that to I see this as a key example in differential equations. And let me show you the function I have in mind. The function I have in mind, I'll call it y, is the integral from 0 to t. Oh, so it's a function of t then, time. It's the integral of this e to the t minus s, some function. That's a remarkable formula for the solution to a basic differential equation. So with this, that solves the equation dy dt equals y plus q of t. So when I see that equation, and we'll see it again, and we'll derive this formula, but now I want to just use the fundamental theorem of calculus to check the formula. As we create it, as we derive the formula, well, it won't be wrong because our derivation will be good. But also, it would be nice. I just think if you plug that in to that differential equation, it solves. Okay, so I want to take the derivative of that. That's my job. And that's why I do it here, because it uses all the rules. Okay, to take that derivative, I notice that t is appearing there in the usual place, and it's also inside the integral. But this is a simple function. I can take e to the t. I'm going to take e to the t outside the integral, e to the t. So I have a function t times another function of t. I'm going to use the product rule and show that the derivative of that product is one term will be y and the other term will be q. Can I just apply the product rule to this function that I've pulled out of the hat, but you'll see it again. Okay, so it's a product of this times this. So the derivative, dy dt, is, the product rule says take the derivative of that. That is e to the t times this, plus the first thing times the derivative of the second. I'm using the product rule. It just, you have to notice that e to the t came twice because it is there and its derivative is the same. Okay, now, what's the derivative of that? Fundamental theorem of calculus. We've integrated something. I want to take its derivative, so I get that something. I get e to the minus t q of t. That's the fundamental theorem. Are you good with that? So let's just look and see what we have. First term was exactly y. Exactly what is above, because when I took the derivative of the first guy, the f, it didn't change it, so I still have y. What do I have here? E to the t times e to the minus t is 1. So e to the t cancels e to the minus t, and I'm left with q of t, just what I want. So the two terms from the product rule are the two terms in the differential equation. I just think, and you saw that the fundamental theorem was needed right there to find the derivative of what's in that box is what's in those parentheses. I just like that use of the fundamental theorem. Okay, one more topic of calculus we need. And here we go. So it involves the tangent line to the graph. It's tangent to the graph. So it's a straight line. And what we need is y at t plus delta t. That's taking any function. Maybe you'd rather I just call the function f. A function at a point a little beyond t is approximately the function at t plus the correction, because plus a delta f, right? A delta f. And what's the delta f approximately? It's approximately delta t times the derivative at t. There's a lot of symbols on that line, but it expresses the most basic fact of differential calculus. If I put that f of t on this side with a minus sign, then I have delta f. If I divide by that delta t, then the same rule is saying that this is approximately df dt. That's the fundamental idea of calculus, that the derivative is quite close, that at the point t, the derivative at the point t is close to delta f divided by delta t. It changes over a short time interval. Okay, so that's the tangent line, because it starts with, that's the constant term, it's a function of delta t, and that's the slope. Just draw a picture. So I'm drawing a picture here. So let me draw a graph of, oh, there's the graph of e to the t. Ooh, it starts up with slope 1. Let me give it a little slope here. Okay, the tangent line, and of course it comes down here. So, not below. So the tangent line is that line. That's the tangent line. That's this approximation to f. And you see, here's t equals 0, let's say, and here's t equal delta t. And you see, if I take a big step, my line is far from the curve. And we want to get closer. So the way to get closer is we have to take into account the bending. The curve is bending. What derivative tells us about bending? That is delta t squared times the second derivative. 1/2. It turns out a 1/2 shows in there. So this is the term that changes the tangent line to a tangent parabola. It notices the bending at that point, the second derivative at that point. So it curves up. It doesn't follow it perfectly, but it's much better than the other. So this is the line. Here's the parabola. And here's the function, the real one. Okay, I won't review the theory there that pulls out that 1/2, but you could check it. Now, finally, what if we want to do even better? Well, we need to take account the third derivative, and then the fourth derivative, and so on. And if we get all those derivatives, then, all of them, that means, we will be at the function, because that's a nice function, e to the t. We can recreate that function from knowing its height, its slope, its bending, and all the rest of the terms. So there's a whole lot more, infinitely many terms. That 1/2, the good way to think of 1/2, 1/2, is 1/2 factorial, 2 times 1. Because this is 1/n factorial times e to the nth, pretty small, times the nth derivative of the function. And keep going. That's called the Taylor series, named after Taylor. And kind of frightening at first. It's frightening because it's got infinitely many terms, and the terms are getting a little more complicated. For most functions, you really don't want to compute the nth derivative. For e to the t, I don't mind computing the nth derivative, because it's still e to the t. But usually this isn't so practical. Line, very practical. Tangent parabola, quite practical. Higher order terms, much less practical. But the formula is beautiful, because you see the pattern. That's really what mathematics is about, patterns. And here you're seeing the pattern in the higher terms. They all fit that pattern. And when you add up all the terms, if you have a nice function, then the approximation becomes perfect, and you would have equality. So to end this lecture, approximate to equal, provided we have a nice function. And those are the best functions of mathematics, and exponential is, of course, one of them. Okay, that's calculus. Well, part of calculus. Thank you.